kids, the first one is chord. Those of you who thought about it, do you agree?
Yeah. No.
Okay, so this is something we haven't actually talked about, but it's probably something you would have learned prior to this class. So it's a segment that has both of its endpoints on the circle. So that is definitely a chord. Okay, how about the next one? What do you think? Diameter. And that is review. We know that a segment that goes through the center of the circle and has both endpoints on the circle is a diameter. Okay, this next one is new. Does anybody know?
Secant.
It is secant. So this is something new to us. A secant is a line that contains a chord. So this is a chord because it has both endpoints on the circle. And if it's a line that contains that, then that's a new word for us called a secant. How about the next one?
Tangent.
Tangent. This is new to us also. A tangent is a line that intersects the circle in only one location. So you can see that this line, it only touches the circle at point A. So that's a tangent. So that's new to us. Okay, how about the next one?
Circle.
A circle.
25.
A circle is a set of all points equidistant from some other point. Okay, how about the next one? Radius. Good. So from the middle of the circle out to the end of a circle is a radius. How about the next one?
Congruent circles.
Congruent circles. As long as they have the same radius, then the circles will be the same size, so they're congruent. And then this next one, how about that?
Concentric circles.
Concentric circles. These are like our dartboards that we were talking about. So concentric circles. Okay, so we did have 3 new words in there. We had chord, secant, and tangent. And we're going to talk more about those as we go. Okay, this page had a lot of it had a lot of old stuff, but a little bit of new. So this first one is a new word. Does anybody know what it is? An inscribed angle. So this is something new to us. An inscribed angle has its vertex on the circle. So an inscribed angle has its vertex actually on the circle. And then its other 2 sides contain chords. And so today we're not really going to talk about inscribed angles, but we will tomorrow, I believe. Okay, how about the next one?
Central.
A central angle. This is something new, or not new. This is something that we talked about last unit. As long as the vertex is at the center of the circle, then that's called a central angle. Okay, how about the next one? Circumference. Circumference is the distance around a circle. How far is it around the circle? So that's circumference. Okay, this next one, cross out that little m. That little m should not be there. That little m stands for measure. And if I want to know the measure of something, I want to know how many degrees it is. And this is not how many degrees it is, because it's talking about a fractional distance. Does anybody know what this is?
Length of the arc.
It's length of the arc, or arc length. So length of the arc, or arc length. So if I'm talking about the distance around a piece of the circle, that's arc length. That's when we set up a proportion if I wanted to solve it. So that little m shouldn't be there because the little m means measure, like how many degrees. And arc length isn't how many degrees. It's like how far is it. Okay, how about the next one?
Arc.
An arc. So any just piece of a circle is called an arc. Okay, how about the next one?
Semicircle.
A semicircle. If we go exactly halfway around the circle, that is a semicircle. Okay, how about the next one?
Minor arc.
A minor arc. If we go less than halfway around the circle, that is a minor arc. And the next one?
Major.
A major arc. If you go more than halfway around, that's a major arc. So a lot of this is review of vocabulary that we talked about the last packet that we did, Unit 7, Part 1, but then we did have some new stuff in here. Okay, are you ready? Well, I think you're going to have to focus a little bit more on this packet. I'm not going to lie. So, if you thought the last one was difficult, I think you're going to find this one to be a little more difficult. And maybe you won't. Maybe you won't. To me, it seems more difficult. So you might have to focus a little bit more. Okay. Does everybody have the packet? The people that just came in, do you guys have the packet? Oh, you have it? Okay. And Colton, you have the packet? Okay. All right. So we're learning some new theorems that we really haven't ever seen anything like or talked anything about. So this first one works two ways. So it talks about in a circle or in congruent circles, two minor arcs are congruent if and only if their corresponding their corresponding chords are congruent. So if I know that this chord here is congruent to this chord here, then I can say this arc is congruent to this arc. So let me write it down and then I'll talk about it some more. So if segment AB, which is a chord, is congruent to chord DC, so if those two chords are congruent, then I can say the two arcs are congruent. So then arc AB would be congruent to arc DC. So this is our first theorem that we have in this packet. So it says if this chord is congruent to this chord, then this arc AB would be congruent to this arc DC. And vice versa. It's going to go the other way too. If I know that arc AB is congruent to arc DC, then I can say that the chords are congruent.
Why did you draw the chord, not the arc?
I don't know.
Okay,
Sorry.
Okay, no.
Let's give him a little curve. Thank you, Adam. Okay, so if we have two chords congruent, then their arcs are congruent, and vice versa. If the arcs are congruent, then the chords are congruent. Okay, this next one, we're actually going to see this one quite a bit in the problems that we do today. This talks about if you have a diameter or a radius. This is a diameter because it goes through the center of the circle, even though you don't see that center of the circle. But if you have a diameter or a radius that's perpendicular to a chord, and you can see that it's perpendicular to the chord because why? How do I know that this diameter is perpendicular to chord DB? Because of that 90-degree angle. So if you see a 90-degree angle, then that means that your diameter or your radius is perpendicular to that chord. So if they're perpendicular, then it bisects the chord and its arc. So this segment here is going to bisect the chord, so DE would be congruent to EB. And then this segment will also bisect the arc, so arc DC would be congruent to arc CB. So this said something about if we have a diameter or a radius perpendicular to a chord, it chops that chord in half, so this piece equals this piece, and it chops the arc in half. So this piece here equals this piece here. So let me go ahead and write that down. So if segment AC is perpendicular to segment DB, then I can say that DE is congruent to EB. That's the chord getting chopped in half. And then the arc also gets chopped in half, so arc DC is congruent to arc CB, or BC, however you want to say it. And this one, like I said, we're going to see this in several problems today. So if we have a diameter or a radius perpendicular to a chord, it chops the chord in half, and it chops that arc in half. And at some point, we might want to think about making some kind of a foldable. I haven't really given it a lot of thought right now, but there's a lot of things in this packet to know. Okay, this next one says, in a circle or in a congruent circle, two chords are congruent if and only if they're equidistant from the center. So if I know that chord AB is the same length from the center as chord DC is from the center, then I can say that those two chords are congruent. So if I happen to know these two lengths, EG and GF, if those two lengths are the same, that means these chords are the same distance from the center. And if the chords are the same distance from the center, then those chords would be congruent. Okay, so if segment EG is congruent to GF, then those arcs are congruent, or the chords are congruent. AB is congruent to DC. So if a chord is the same distance from the center as another chord is, then those two chords will be congruent. I don't know. I just ended up putting something else on there, like x to the 5th, meaning, take x times itself 5 times. No. I don't know. I said, let's just make up an example, like x to the 5th. And what does that mean? Yeah, that's what I did. Fine. Okay, this next problem is a little proof, but it's not that bad. We're just going to kind of talk about some of the things that we just talked about. So we're given circle M, and we're given that arc AC is congruent to arc NR. So arc AC is congruent to arc NR. I'm going to give each of those a little tick mark. And then this is what we're going to try to prove. So let's just look at what they've put down here on the proof. First thing says exactly what the given said, so that's why it says given. Step 2 says that chord AC is congruent to chord NR. Do you know if any of these theorems up above here let us know that?
Yes.
In the first statement, we're told that this arc is congruent to this arc, and now it's saying that this segment AC is congruent to this segment NR. Why do you think, Austin? Because of the first theorem. Can you guys stop talking back there, please? In the very first theorem, it said if we have two congruent chords, then their arcs are congruent. And then I also said it works the other way. If you have two congruent arcs, then the chords are congruent. And that's what we had here. In the given problem, we were told that these arcs are congruent. So if the arcs are congruent, then their chords are congruent. So that's why I can say it. So I'm going to say if your minor arcs are congruent, then chords are congruent. So if your minor arcs are congruent, then your chords are congruent. And vice versa. If the chords are congruent, then the minor arcs are congruent. Okay, this next one says that segment NM is congruent to RM, which is congruent to AM, which is congruent to CM. What are all of those guys? Yeah, they're all radii, right? They're all a radius. NM is a radius. MR is a radius. MC is a radius. MA is a radius. Should all the radiuses have the same length?
Yes.
Yeah. So I'm going to give them all 3 little tick marks. And the reason I'm going to put for that is all radii.
Why does it say radii? Why is it radius?
Because it's the plural form. All radii of a circle are congruent. Whatever one radius is, the other radius should be the same measure. Okay, and then this takes us back in time to why triangles are congruent. So this next statement says that triangle RNM is congruent to triangle CAM. And why do you think? Side. Okay, so the whole point of this proof was just to talk about some of the things we talked about just a second ago. So if you have if you have two arcs that are congruent, then their chords are congruent. And then I know that all radii should be the same length, and then that led me to the triangles being congruent by side. Okay, let's just look at some specific problems, and we're going to practice some of those things that we just read about. Okay, first thing, recreation. Dennis, he built a sandbox in the shape of an octagon. Sounds fun, right? The segments drawn in the diagram represent the supports he used to frame the sandbox. These supports are diameters of the outer circle and create 8 congruent central angles. So all of these angles here, they're all central angles because their vertex is at the center of the circle, and it says that they're all congruent. My ultimate goal is to figure out the measure of angle SXW. I want to figure out that little angle right there. Let's start with the angles in the center. How could I figure out what each of these angles are in the center of the circle? Anybody have an idea how I could figure out what each one of these angles are in the center? I know they're all congruent.
Well, you can do the area of you can do the angles of octagon. Divide it by sides. You can do that,
I'm going to draw you something.
You could always do 8 minus 2.
What's that?
A circle.
And what do you know about
360.
what do you know about the degrees in a circle?
360.
And so if there's 8 angles, okay, so let's take,
Well, that's what I was trying to say.
it's okay. So let's take 360 divided by 8. Can somebody do it and tell me what you get?
45.
Okay, 45. So that means all those angles inside are 45. Okay, I am going to take this triangle right here, and I'm going to just blow it up down here. Shoop, shoop, shoop. So we just learned that each of these angles in the center are 45 degrees. So that little guy up here is 45 degrees. And then let's talk about this segment here and this segment here. These segments have a name. What are these called? What'd you say? What'd you say? Yeah, they're legs of the triangle, but there's something vocab-wise that we talked about on the... Yeah, they're radii. From the center to an edge of the circle, from a center to the edge, these are both radii, right? So should they be the same length?
Yeah.
Okay, so I'm going to give them each one tick mark. Now let's talk. What do you know about the 3 angles in a triangle?
Equal 180.
They add to be 180. And do you guys remember that whenever you have an isosceles triangle, that the angle across from that congruent side is congruent to the angle across from that one? So if I wanted to figure out what each of these are, what would I do?
Dude, 180 minus 45.
180 minus 45. Okay, what's that give us?
By 2.
Yes, divide by 2. What's it give you?
135.
135. And then that's what both of these are. And if they're both the same, I want to divide that by 2, which is what?
60 something 25.
67.5. And so if I was to bubble this in, I would bubble in the plus and then the 67.5. I'm not actually going to take the time to bubble the 6, the 7, the decimal, and the 5, but that's how I tend to do it. Okay, so that takes us back to basically things that we've learned throughout the year. Okay, this next one, this is something that we learned today. So it says circle N has a radius of 36.5. Where do you guys see a radius in this picture?
HM.
HN is a radius. Anywhere else? NG is a radius. Okay, so those both will be 36.5. I'm going to hang on to the HN for a second because it doesn't make it real pretty to write that that's 36.5, but I do know that NG is 36.5. Okay, then it says that radius NH is perpendicular to chord FG. Okay, we learned something just a minute ago on the front page about that. If you have a radius or a diameter perpendicular to a chord, what did we learn? Let's go back and look.
They have the 90-degree angle and it bisects.
We learned here that if we have a diameter or a radius perpendicular to a chord, that it chops that chord in half, so that's why both of those are the same, and it chops the arc in half, so that's why both of those are the same. Okay, so that was our second theorem. So let's look at this. So since I know that this radius, NH, is perpendicular to this chord, it's going to chop this chord in half. So what's congruent to what?
FH is congruent to HG.
Okay, so the arc, FH, is congruent to HG. And what about the chord?
Same.
FZ is congruent to
ZG.
ZG. There's a little more talking than I want to have go on because, like I said before, this is a little more complicated, I think, than that packet that we did, that we just finished. Okay, and then it tells me that it was perpendicular to chord FG, and it says that was 53 centimeters long. So if FG is 53 centimeters long, can we figure out how long FZ is? FZ, I would divide that by 2. And what does that make it?
26.5.
26.5. So if that's how long FZ is, how long is ZG? 26.5. Okay, so that's just some stuff that I know because it told me that FG was 53 centimeters long, and I know that that got chopped in half. Okay, let's look at A. A says if the measure of arc FG is 85, find the measure of arc HG. So divide by 2. If the whole arc is 85 and I want to find just this piece of it, I want to divide by 2, right? So let's take 85 and divide by 2. What'd you say?
42.5.
Okay? And then this next one wants me to find the measure or the length of NZ. Okay, I'm going to take this triangle right here and I'm going to blow it up.
They're congruent. Right, and Z, right?
A squared plus B squared equals C squared.
That's what we're going to do. So here's my triangle, NZG. This was a right angle. How long did we say NG was? 36.5. Okay, we're trying to figure out NZ. I'm going to call that X. And then somewhere we said how long ZG was. How long did we say ZG was? 26.5. Okay, so I heard Austin say A squared plus B squared equals C squared. Do you guys agree? That's right. We have a right triangle, and so I'm going to use Pythagorean theorem. Which one's the C?
The 36.5.
Okay, so that's going to be the equals C squared part. So we're going to have X squared plus 26.5 squared equals 36.5 squared. Take a moment and figure out X. And you can give it to me as a decimal.
Figure out the square of 36.
Oh, right there. Relax. Okay, take a moment and calculate what X is. And you can round to the nearest tenths. That'll be fine.
25.1.
To Austin it is.
What? I have no clue. There it is.
Good thing.
I heard stutter. That's really all I heard, to be honest. Yeah.
Do you need me to show you in the calculator at all?
I don't have to. Shut up.
So in my calculator, I'd probably put 36.5 squared minus 26.5 squared, and then I'm going to square root that answer. So, did everybody get 25.1 if you round to the nearest tenths? Okay, so we are going to see some Pythagorean theorem creep back out, but that's not too scary, I don't think. Okay, this next picture is missing a right angle. It should have been in the picture, but it didn't get copied very well. This little guy right here is a right angle, and this little guy right here is a right angle. So go ahead and put those right angles in your picture. And let's just talk about that for a second. If I were to continue to draw this, is this right here a diameter? If I continue to draw it? So we learned a minute ago that if you have a diameter perpendicular to a chord, what does it do to the chord? Well, yeah, it's perpendicular, so that's where the 90-degree angle is. But if it's perpendicular to the chord, what's it do to the chord? Yeah, it cuts it in half, so it's going to make FN congruent to NG. And that's going to happen over here, too. This diameter is perpendicular to this chord, so it's going to cut this chord in half. So this segment here is going to be congruent to this one. And also, what does it do to the arc?
Bisects.
It bisects it. It chops the arc in half. But I'm going to wait to see if I need to know that, just because I don't have that segment all the way there. Can you guys please stop talking back there? Okay, looking at this, it says chords FG and LY are equidistant from the center. Okay, we learned something on the front page about that. See if you can find it. Chords FG and LY are equidistant from the center. Let's look. If two chords are equidistant from the center, where do you see it? Theorem 1, Theorem 2, Theorem 3. Theorem 3. And it says that if two chords are equidistant from the center, then what do you know about those chords? They're congruent. If two chords are equidistant from the center, then they're congruent. So I know that since FG is the same distance from the center as LY, that FG is congruent to LY. So that's one thing I know. Okay, let's talk about the radius. If the radius of the circle is 32, my goal is to figure out how long FG is, and my goal is to figure out how long BY is. Okay, so if the radius is 32, where do you guys see a radius?
FM and LM.
Okay, FM is a radius, so that's a 32, and LM is a radius, so that's 32. one of the things it wanted me to find was FG. So let's talk about finding FG. FG is this whole piece here. If I found this half of it, could I then know the whole thing?
Yes.
Okay, so I am going to blow up this triangle right here. Off to the side, choop, choop. And that's FNM. FNM. Okay, so let's talk about it. How long is FM? 32. How long is NM? 22. So let's figure out how long FN is. What would I do?
You would say 32 squared minus 23 squared.
Yeah. I would do Pythagorean theorem, which is x squared plus 22 squared equals 32 squared. Okay, take a moment and figure that out, and you can round that to the nearest tenths.
23.2.
Do I need to show anybody in the calculator? What'd you say again, Austin?
I said it was 23.2.
23.2. Okay, so if Fn right here is 23.2, how long would Fg, the whole chord, be?
46.4.
46.4, because it's twice that. So, I should put squiggles. So it's approximately 46.4. And since I know these two chords are congruent, that's how I know that this whole length is the same as this length. So if I wanted to know how long BY is, how long is BY? Is this chord the same length as this chord? So if this chord is 46.4, this chord should be 46.4, right? So what would BY be? 23.2. It'd be half of that. Okay, how are you feeling so far? You don't like it? Well, I'm telling you now, this packet isn't as easy as the last packet, and you're going to have to focus more, so I'm going to be a little bit more mean about people talking while I'm trying to teach. So, one thing about the problems is they're so small, it's hard to work with them. And so that's one reason why I keep taking pieces of the problem and putting them off to the side so we actually can look at it a little bit better and we can do a little bit more work with it. So I just want to talk about those three theorems just a little bit more. So the third theorem was in this problem. If we have a chord that's the same distance from the center as another chord, then I know those two chords are congruent. So that was the third theorem. The second theorem we've seen a couple times already. If we have a radius or a diameter that's perpendicular to a chord, it chops that chord in half, so that piece would be the same as that, and it chops the arc in half, so that piece of the arc would be the same as that. And then the first one that we learned about, we talked about in this proof here, and that was if we have two congruent arcs, then their chords are congruent, or if we have two congruent chords, then their arcs are congruent. So those are the three things that we've learned just in this lesson. Okay, I want to do one more problem with you. This would actually be your homework, but I want to go ahead and do it because it's kind of ugly. So it's the next page, page 5, and I want to do the 9 through 14 with you. Well, I'm going to do 9 through 14 with you, and then that's going to leave you 12 little problems, which I think are easier than the 9 through 14. Okay, so looking at the 9 through 14, it tells me the radius of circle Y is 34. Okay, let's look at our picture. Do you guys see a radius in here? Okay, YC is 34. I'm just going to go ahead and I'm just going to write it off to the side, just because it's kind of hard to write down that that is 34, but that's how long it is. Okay, then it tells me that AB is 60. Let's talk about that for a second. Do you see something in this picture we learned about in one of those theorems? The second theorem said that if you have a radius or a diameter perpendicular to a chord, what does it do to that chord? Cuts it in half. So AD would be congruent to DB. Okay, so let's talk about AB being 60. If AB, this whole chord here, is 60, what is AD? 30. And what's DB? 30. And it's going to probably be really helpful that you guys draw in your pictures for this lesson. Okay, and then it tells me that the measure of arc AC is 71. So the measure of arc AC is 71, and that is in degrees. It just doesn't have the degree symbol there. Okay, so let's talk about that for a second. not only if you have a radius perpendicular to a chord does it chop the chord in half, it also chops the arc in half. So this arc gets chopped in half. So arc AC would be the same as arc CB. So what is arc CB? Okay, let's fill out what we need to know, and then we'll see if we need to figure out anything else. Okay, so number 9 says, what's the measure of arc BC? And what's the measure of arc BC? 71. Okay, number 10 wants to know what's the measure of arc AB? 142, because it's 71 plus 71, so 142. Okay, number 11 wants to know the length of AD, and I know it's length because there's no little m, and if you don't see a segment symbol or a line symbol, it means length. So what's the length of segment AD? 30. Okay, number 12 wants the length of segment BD, 30. So not so bad. Okay, and then 13 wants the length of YD. This length right here.
17.
Why do you think 17? Because what? So, did we ever talk about the radius gets chopped in half?
No.
If we have a radius perpendicular to a chord, the chord gets chopped in half, and the arc gets chopped in half, but that doesn't mean the radius gets chopped in half. A couple things about this packet. There's a lot of pictures that don't look like they should. So I know this segment here looks the same as this segment, but it's not. So it's not the radius that gets chopped in half, it's the chord that gets chopped in half, and it's the arc that gets chopped in half. But I'm going to draw something right here. Do you know what this is that I'm drawing right here?
A triangle.
Yeah, but what's this segment right here that I'm drawing?
The hypotenuse.
It has a name. A radius. It goes from the center to an edge. That's a radius. Okay, what did we learn about the length of the radius? But the radius is 34. So let me put that 34 there. I'm going to blow this guy up. Okay, so I'm going to take him down here, and I'm going to blow him up. I know that this is Y, this is A, and this is D. We just talked about YA as a radius, so YA is 34. A minute ago, we talked about this chord getting chopped in half, and how long was AD? 30. And I now want to know how long YD is, so I'm going to call that X. And I know that these are perpendicular, so there's my 90-degree angle. So what do you think you do?
Pythagorean theorem.
Pythagorean theorem. Which one's the C?
34.
34. So it's going to go X squared plus 30 squared equals 34 squared. Go ahead, work that out. Give me a decimal.
16.
It came out exactly 16?
Yeah.
Well, let me get rid of my squiggles then. So it came out to be 16, and that is the length of YD, which is what this wanted to know over here, is how long is YD, which is 16. Okay, so YD is 16, and how long did we say YC was?
34.
YC is 34 because it's a radius. So if I just figured out that X is 16, how could I figure out DC? How long is the whole thing, YC?
60.
34 because it's the radius. And how long is this piece right here, YD? 16. So how could I figure out the DC? Subtract. So 34 minus 16, and that makes how much? 18. So they're close to being congruent, but they're not. So it's not the radius that gets chopped in half, it's the chord that gets chopped in half. So this piece of the radius is 16, but this piece of the radius is 18. So the radius doesn't get chopped in half, it's the chord that gets chopped in half. Okay, so you guys need to try to do the 1 through 8 and the 15 through the 18. And I think they're easier problems than this one that we just looked at right here. So that's your assignment for tonight, is to try the 1 through 8 and the 15 through the 18. And we'll see how you do with that.
So if you take any